This is the third and final installment of our power lectures. And so in the first two parts, we were talking about one-sided tests, right? Now we're going to be talking about two-sided tests. So this is really just a review. You all know that when we do two-sided tests, we have alpha over 2 and those rejection regions. So we have 2 rejection regions now instead of 1 that we had with the one-sided test. And you should be able to calculate your upper and lower bounds for those rejection regions in a two-sided alternative just like this. All right, so when we're looking at power in a two-sided alternative, right, we have some underlying truths, some underlying distributions that we don't know what these are, but we're going to draw them out and figure out then what our power is in our expressions for beta using some equations. All right, so remember we have 2 rejection regions now. So when we look at power, remember power is the probability that given that HA is true, which is all this under this line, given that HA is true, what's the probability that we're going to reject H naught? And so it's any of this striped area, right? HA is true, we're in the rejection region here. Well, it's also another region, right? Here, HA is true over here, and we're also in a rejection region. So there's a teeny tiny bit of area under the curve here that we should technically take into account for the power as well. But you can see that the area of that is so small that it's negligible, and we usually just neglect it. So let's go through and look at the power equation now. So remember, 2 rejection regions. So power is 1 minus beta. And so we get the area under the curve. Let's see, this is on the right tail side, and this is on the left tail side. And then we go, and these are just algebra expressions, okay? And I wanted to say, right, this is on the left side of those graphs here, right? And this is very, very small. This is big, and this is bigger compared to this. Okay, now we're just going through some algebra and figuring out an expression for power here. Okay, so just algebra like we've done lots of times before, and we're getting these equations then. Okay, let's see, what did I want to point out from here? I guess really nothing. So this is just one side for the power, and then this is the other side, and then we've used this identity here that phi is the normal cumulative distribution function, and we've also used it here as well. And so we get power is 1 minus beta is equal to these 2 values right here for a two-sided alternative. Right? It looks a lot like it did for a one-sided alternative. The only difference, well, I'm sorry, a lot like it did for a one-sided alternative, but we have 2 terms here. And we have 1 minus alpha over 2 versus 1 minus alpha like we did before. Okay, so these are just the expressions from the last slide. And then we're going to make a substitution here. We're going to replace 1 z 1 minus alpha over 2. I'm sorry, z 1 minus alpha over 2 with, we're going to place the negative of z 1 minus alpha over 2 with z alpha over 2. And we do that in these 2 terms here. Okay, whenever mu1, okay, that underlying the mean of the underlying alternate hypothesis is less than the mean of the underlying null hypothesis, whenever mu1 is less than mu0, then the second term is negligible. But if mu1 happens to be bigger than mu0, then the first term is negligible. So when we do that, then these two-sided power equations, it's going to reduce just to here, okay? It depends on which one is true, but it'll always reduce to this when we're using absolute values. So this is the expression for power for a two-sided test. And if we compare it to the expression for power using a one-sided test that we derived in part 2, we see that they're very similar. Only difference now is that we have alpha over 2 compared to alpha. And we don't have 2 terms in this anymore, right? Because we said that one of these terms is negligible and it can just reduce to this term. So really similar expressions. Only difference is alpha over 2 in the two-sided one and alpha in the one-sided one. Okay, so now that we have two expressions for power, we can relate the power to the sample size. Let me just go back to those power expressions now. You see that we can relate power to the sample size, which is really important because we often we'll choose a power level up front, and then we'll often figure out, well, okay, how many samples is required to accomplish getting a power of that size. Okay, and sometimes though it's the reverse. Sometimes budgetary constraints, they determine what sample size we're going to be able to get, and then we use that sample size and say, well, okay, what kind of power could we detect using that sample size? And so those are really important things to contemplate. If you're in a company, you're actually doing an experiment, right? You have to be able to determine, either what's the sample size that I need or what power can I expect given my sample size. So then we're going to look now at, how can we use that power expression to get to the sample size that we need? And so the first one we're doing is, how do we figure out the sample size for a one sample test of continuous data that's a one-sided test? And we can just go and we use our power expressions that we derived here before. Hang on, I'm a little confused here because I'm seeing Z1 minus alpha. Okay, yes, okay. So here is our expression for power for a one-sided test. So we do have Z1 minus alpha. Okay, so when we look at a one sample test of a continuous data and it's one-sided, we have this expression for our power here. And then we're just using some properties that we've used many times before, okay? So instead of the power here is, we're just rewriting this, is phi z1 minus beta, okay? 1 minus beta is equal to phi z1 minus beta. Okay, and then we just kind of are looking at all these things going through here. Then we can find that n is equal to this expression now. And so we can figure out, if we have a certain power, which is 1 minus beta, right? What sample size do we need? Okay, so that's a one sample test of continuous data that's one-sided. We do very similar algebra to get to a one sample test of continuous data that's two-sided. So really, we had alpha over here before, and now we just have alpha over 2. So just a quick look back. We had alpha over here, and now we have alpha over 2 in the two-sided test. So not much difference, but it is a difference when we figure out n for one-sided versus two-sided. Okay, so I want you to be able to look at this equation now. This is the two-sided test, right? And say, well, how do our design parameters affect how big of a sample size we need, right? If we want larger power, we need a bigger sample size. If we want to have a higher alpha, right, instead of maybe 0.05, we make it 0.1, well, then we don't need as big of a sample size. And remember, if our effect size increases, which is the difference between the means of the alternate and the null hypothesis, right, if that's a big effect, if we have a big effect size, then we don't need as big of a sample either. And then finally, if our variance is going to increase, well, then we're going to have more overlap, right? And that always means that if we have more overlap, then we'll need a bigger sample size. Otherwise, we'll get a lot of errors. Okay. And so, yeah, so this slide is just talking a little bit about the n, the alpha, the beta, and the variance, and the effect size. They're all related in this one equation, right? So if we set for those parameters, we can solve for the other one. And what do we most typically do? A lot of times we'll typically set alpha, right? We've been doing that a lot. And we can kind of figure out what the variance is sometimes just by our samples, right? And then we're going to solve for the sample size if we also set the power and the anticipated effect size. And power is something we can set also. An anticipated effect size has to come from, maybe we've done some small sample measurements and we can anticipate what kind of difference in the null and the alternate hypothesis means will be. Okay, so that's typically what we'll do, but we could also solve for power if we're given a feasible sample size and an anticipated effect size, or we could also solve for effect size if we're given a feasible sample size and a desired power level. So we can use it in lots of different ways. Let's just go through an example, because that's a good thing to do to figure out how to use this equation. So here's an example from Rosner, and it's considering the effect of a calcium blocking channel agent on heart rate for patients with unstable angina. Here we're going to set the power at 80%, and we're also saying that we want to detect a significant difference if the effect of the drug is to change the mean heart rate by 5 beats per minute. Right, so the mean heart rate is changing, so that's the effect size. mu0 minus mu1 is 5 beats per minute. And then it says in either direction, right? So we're thinking, okay, this is two-sided test, and we happen to know sigma, which usually we can estimate that through a sample size, but we'll say we know sigma here. Okay, and how many patients? We want to say like, okay, if that's what we can expect, how many patients should be in this study? We know how to figure this out. We know how to figure this out too. Remember that beta now is 0.2 here because the power is 80%. So Z1 minus beta is Z of 0.2, and you can figure that out. We're given this, our effect size is 5. It tells us that we need 31.36 patients, but we can never have a third of a patient, right? So we're going to round up and say that we need 32 patients for this study if we're going to detect a significant difference. Okay? If it happened to be a one-sided study, we'd need fewer patients. We'd need just 25. The difference would be that this would be Z1 minus alpha. Okay? All right. We can also figure out the value of n if we do if we're doing a one-sample binomial test that's two-sided. Okay, we find that this is an expression for power. We do the same type of thing that we did to figure out the expression for power when we assumed a normal distribution. We're also assuming a normal distribution now for the binomial test, right? And then we're saying, like, which I should say here, this is the one sample binomial test normal distribution, right? If we have a normal distribution, we can use the same methods and we get this expression for power. Okay, we just solve it for n, and then this will tell us what sample size do we need. So everything we talked about to this point were just for one sample test. Okay, and the same total logic, right, is going to apply to two sample tests. So we're going to go through these without proof, but I'm just going to give you the results for doing two sample tests. Okay, so if we have two normally distributed samples now of equal size, and if we have a two-sided test with this significance level alpha, power 1 minus beta, this is how we determine the sample size in each group. Okay, and here delta is just the absolute value of the effect size. We're squaring it anyway, it doesn't matter if we have absolute value or not. Oops. But remember I've told you before that a lot of times when we're comparing two samples, we don't have to have equal sizes. We can do unequal sizes. And if we do unequal sizes, then these are expressions for how we determine the sample size in one group and the sample sizes in another group. In this K is something that I haven't seen before, where it's the projected ratio of those two sample sizes. Okay, and I didn't give you the expression for power under those conditions, and this is how the expression for power under that condition where we have two normally distributed samples. Okay, so one more example. We want to compare we want to determine sample sizes for this problem, and in this problem we're going to determine equal sample sizes. to compare blood pressure data for oral contraceptive use and non-oral contraceptive use. So we get some pilot data, and we put that into our expression here. So notice that now that when we used our pilot data, instead of using sigma, I'm just using the pilot data for the underlying population variances. That's typically what we do. We're making a lot of estimates when we do these. These aren't perfect numbers at all, but we're just saying like about what size sample do we need. So we're estimating these with the sample variances. We've figured out these before. And the effect size here, we're estimating the effect size from our sample. So the effect size is about 133 minus 127 or so, and then we're going to square that. And we find that, wow, we need a pretty big sample. We need 152 people now in each group if we're going to get a significance level of 0.05 and a power level of 0.8. All right, the next slides are just kind of showing the results of some things, like how could you figure out n if you're comparing two binomial proportions that are two-sided. Not going to go through it, but I know that you can figure this out. And remember that k is the ratio of n1 to n2. All right. Here's a power expression for that. And that's pretty much it then. Okay, so those formula that were given to you, they apply when the variance is equal or unequal, right? Remember before when we had to use we had to use the F test to figure out if variances are equal or unequal. But we don't need to do that here. And we don't even need to use the t distribution here. All those things, we're using the z rather than the t, and that's all okay because all these things that we're putting in here are assumptions anyway. So whatever we're getting is really just an estimate. So we've made a lot of estimates when we try to figure out the sample size. When we find n, we also assume a given effect size. And a lot of times it's easy to anticipate you're going to get a bigger effect size and then you need a smaller sample. You're going to get it's easy to, anticipate a bigger effect size than actual. And if you do that, because you can say, oh, well, then I need a smaller n. But if you do that, then you might have an underpowered study, it's called. So resist that temptation to say, oh, we're going to have a really big effect size. You have to kind of look at your discipline and figure out what kind of effect size they usually determine or estimate. And then, just doing all this analysis up front, it's really important because it's going to help you avoid wasting resources. So if you do these calculations up front, you're going to be, you'll have a better chance that you're going to get results that are unequivocal. So anyway, I guess the second thing is just, work out these things beforehand because that's doing good science.